You know what I was thinking? If it wasn't for the great minds like that of Aristotle, Galileo, Newton, or the great Euler for that matter, we probably would not have been able to send humans to moon, or drive a cool car like this one, or go for a fun roller coaster ride at Six Flags, or go up and down a 100-storied structure using an elevator. It was these great minds that laid solid foundation to the branch of science called as mechanics that governs most of the modern macroscopic world as we know it today. In this video, we'll talk about mechanics, we'll see two aspects of mechanics which are kinematics and kinetics, and explore branches of mechanics. We'll see how we idealize various systems based on their complexities, and finally summarize everything that we have covered. Welcome to my channel. So what is mechanics? Mechanics is a branch of science, particularly physics, that deals with the state of motion of an object or objects that are subjected to external forces. Now I want you to observe two things in this definition. The first objective of mechanics is to define the state of motion of an object. A particular case of this is the state of rest. And the second objective of mechanics is to understand the cause of motion. That is, what are the external forces that lead to change in the state of motion of an object, which are the external forces. Now, in order to understand this definition better, let us consider two examples. Now, consider this toy car. This car is currently in the state of rest. Now, that does not mean that there are no external forces acting on this body. Clearly, when I leave this object, it falls down. That means there is a downward gravitational force acting on this. However, when I place this object on the table, it is at a state of rest. And you might wonder, why is this not falling? That is because the normal reaction from the table on which this object is placed balances the downward force of gravity acting on this body. And therefore, the object is not moving and hence state of rest. Now, when I apply a force in the forward direction, this object accelerates. That is, the force that I have applied on this body is instrumental in changing its state from that of rest to that of accelerated motion. Let us now consider a more complex example. We have a rigid ball lying on my hand, and clearly this ball is in a state of rest. And that is because the downward gravitational force acting on the ball is balanced by the upward normal resistance of my palm. Now, when I apply an external torque, which is a form of an external force, this ball rotates about its axis of rotation. Now, clearly, it is the external torque that is instrumental in changing the state of the motion of this ball from that of rest to having angular acceleration. However, you might wonder onto why this ball comes to a halt after a couple of rotations. And that is because this ball is in contact with my palm, and therefore there is a frictional resistance between my palm and the ball. So when the ball rotates, as a consequence of this frictional resistance, it slowly comes to a halt. Therefore, it is this frictional resistance that brings the ball from a state of having angular acceleration to the state of rest. Just like these systems, mechanics can explain many other macroscopic systems. And those systems can be as simple as point object or could be as complex as fluids. Understanding the mechanics of any system requires two major efforts. The first is kinematics and the second is kinetics. Kinematics deals with the study of motion without any consideration to the cause of motion. The questions that you would ask if you were to investigate kinematics of any system are like, what is the configuration of the system? What is the position of the object? What is the orientation of the rigid body? Or what is the linear or angular velocity of the system? Or what is the linear or angular acceleration of system? And so on. In summary, kinematics deals with the geometry of motion and ignores the forces that are causing the motion. On the other hand, kinetics deals with the forces acting on the system. These forces could be external forces like that of gravity, or they could be internal forces like that of tension in the cable, or the spring force in the deformed spring, or they could be inertial forces in the dynamic system. Now, if I were to consider the kinetics of this rubber band, I would very quickly realize that in the deformed state of this rubber band, there are two forces acting on the system. First is the external force applied by my hand, which leads to elongation of this band. And as a result of this elongation, this band develops an internal resistance. And clearly, the internal resistance of the band balances the external force that I have applied that leads this object to be in the state of rest while being deformed. Broadly, mechanics can be divided into two branches. The first is statics and the second is dynamics. Now let's look into each of these branches. Statics deals with the equilibrium of objects that are at rest or traveling at a uniform velocity, that is, traveling in the straight line with constant speed. Now there are two things that I want you to observe in this definition. The first is that the object in static equilibrium need not be in the state of rest. The only requirement is that it needs to travel with the uniform velocity. That is, it should not change its direction while moving and it should maintain constant speed. You will observe that the object at rest is a special case of the object traveling at a uniform velocity. And this is because the object at rest has zero velocity and the velocity does not change with time. The second point I want you to observe is that the object traveling at a uniform velocity does not experience any change in its state of motion. Now this is because the object traveling at a uniform velocity maintains its direction of motion and also the speed. This does not mean that there are no external forces acting on the system. You can have external forces acting on the system. However, the only requirement for static equilibrium is that the sum total of all the external forces acting on the system must vanish. Now let's look at the case of uniform velocity. Consider that you want to drive a car in the straight path and maintain its speed. Even to maintain the constant speed of the car, you have to press the accelerator. And this is because when the car is traveling in the forward direction, it is acted upon by the frictional force in the direction opposite to that of its motion. And therefore, the engine has to continuously apply the forward external force to counter the frictional force. So as you will see, in the horizontal direction or in the direction in which the car is traveling, the frictional force is balanced by the external force applied by the engine, whereas in the vertical direction, the weight of the car is balanced by the normal reaction. This is a classic example of the object in static equilibrium traveling at a uniform velocity. To sum up, when the object is in the static equilibrium, the sum total of all the forces acting on the object becomes zero, and by extension, the object is not accelerating. Unlike statics, dynamics deals with the accelerated motion of bodies. In a dynamic system, the sum total of all the external forces acting on the object is not equal to zero. That is, there is a net non-zero force acting on the system, as a consequence of which the system experiences a change in its state of motion by virtue of acceleration. However, just like us humans, every object or system is lazy and resists the change in motion. And this resistance to the change in motion gives rise to inertial forces. And therefore, in a dynamic system, one must consider all the external forces as well as the inertial forces. To visualize a static and dynamic system, let us consider an example of a football or soccer, depending on where you are. While the ball is lying on the ground, waiting to be kicked by the player, it is in a state of static equilibrium. This is because the downward gravitational force is balanced by the normal reaction of the ground, and the net resultant force is zero. However, as soon as the ball is kicked by the player, it becomes a dynamic system. The kick imparts a net non-zero force to the ball, as a consequence of which the ball goes from the state of rest to having acceleration in the direction of force. To initiate the discussion about idealization of systems in mechanics, let us consider our mighty blue planet Earth. Clearly, this is not blue, but we'll make it work. Let me ask you this. Would you model planet Earth, which has radius of 6,400 kilometers, as a point object, or a rigid body, or a deformable object? Well, as you will see, systems in mechanics have very wide range of complexities, and they can be modeled accordingly. Broadly speaking, mechanical systems can be classified into four classes. The first is particle. A particle is a point object that is characterized by its mass. It does not have any shape, and therefore there is no question of its spatial orientation. When you model something like a particle, you assume that all the mass of that system is concentrated at a single point. For example, if you were to model the orbital motion of the planet Earth around the Sun, you can model the planet Earth as a point object. The second type of mechanical system is a rigid body. Unlike a particle, a rigid body has well-defined shape, and therefore it has spatial orientation associated with it. As the name suggests, a rigid body is rigid, that is, it cannot deform. Mathematically, what that means is the distance between any 2 points in the rigid body remains fixed over time. For example, in addition to the orbital motion of the planet Earth around the Sun, if you were also interested in modeling the rotation and wobbling of the planet Earth, you can model it like a rigid body. The generalization of the rigid body is the deformable body, and therefore it has all the characteristics of the rigid body except for the fact that a deformable body can deform under an application of external force. For example, if you are interested in modeling the plate tectonics of the planet Earth or modeling the shockwave propagation as a result of a meteorite's impact and earthquake, you would model the planet Earth as a deformable body. Unlike solids, fluids can flow. Fluids do not have well-defined shape, and this is because they cannot resist shear force. For example, if you were to model the ocean currents, you would use the principles of fluid mechanics. Among all 4 systems that we have seen so far, in my opinion, fluids are the most complex to model. To an extent that the Clay Institute of Mathematics has a $1 million worth of prize to investigate Navier-Stokes equation that governs fluids, especially in case of turbulence. The existence and smoothness of the solution to Navier-Stokes equation is not yet well understood and still an open-ended question. So, I've given you a simple and a not so simple way to become a millionaire. Now we come to the final and the most important part of the video where I summarize everything that we have seen so far. How about we go for a rapid flashback of everything that we have covered so far. We started with mechanics and we realized that mechanics has 2 objectives. The first is to define the state of motion of an object, and the second is to understand the cause of motion. We saw that mechanics has 2 aspects. The first is kinematics and the second is kinetics. Kinematics deals with the motion of an object irrespective of the forces acting on it, whereas kinetics deals with analysis of all the forces acting on the object. We also saw that mechanics has 2 branches. The first is statics and the second is dynamics. Statics deals with the equilibrium of objects that are either at rest or are traveling at a uniform velocity, whereas dynamics deals with the accelerated motion of bodies as a result of net non-zero external forces acting on it. Depending on the complexity of the mechanical systems, the study of mechanics can be divided into 3 parts. The first is the mechanics of particles, the second is solid mechanics, and the third is fluid mechanics. Solid mechanics can be further divided into mechanics of rigid bodies and the mechanics of deformable bodies, whereas the fluids can be divided into compressible fluids and incompressible fluids. And all these subjects can be broken down into statics and dynamics. Well, this brings us to the end of our discussion, and I certainly hope it was helpful. I'll also be posting all the notes to my website, link down below. And thank you very much for sticking around. If you enjoyed the video, give me a thumbs up and do not forget to subscribe for upcoming content. Until then, more power to you.